going to talk about is active devices.
You do?
As opposed to what you talked about, well, I'm going to do something on the board.
Okay, yeah.
Previously, we talked about passive devices, resistors, capacitors, inductors. Passive because they don't really do anything, they don't change states. You know, a resistor just sits there, you pass current to it, make it warm, but really doesn't do anything. What we're going to talk about tonight is some actual active devices that actually do something, control something, or actually change their state. So to start off, we're going to talk two things we've talked about so far. One end of the scale, we'll say we have insulator, and the other end of the scale, we'll say we have conductor.
Would you be able to just pull that?
Yeah.
Over
This one a little bit.
Thank you.
So typically, an ideal conductor would be copper or silver, something like that. The ideal one would be resistance of 0 ohms. At the other end of the scale, an insulator, glass, whatever. Ideal insulator would be infinite ohms. So tonight we're going to talk about something that falls in the middle. Semiconductor. It's in the middle. It's not a good conductor. It's not a good insulator. Now how do we do that? Control. I should just okay. So to make a semiconductor, we take, the most common is silicon. Silicon in pure form, like your silicon rubber, silicon, which is basically sand or whatever, is normally, it's a good insulator. But by modifying the chemistry with a process they call doping, so we either create a part of silicon that has extra electrons. Okay. So if we dope it and modify it in such a way that it has some extra electrons, they'll likely have a net negative charge, or what we call N material. Likewise, if we remove some electrons, and so therefore it's short of electrons, it's going to have a net positive charge. So likewise, we're going to call it P material. So we take two pieces and we're going to combine them. When we join them together, we got P material, N material, and then there's what we call a PN junction. So when we just put them together, in the middle, in this middle zone, basically any loose electrons will cross over and fill in basically the holes. So in this middle section, we'll call it the depletion zone. They'll basically have no charge. They'll all be satisfied that our missing electrons, we'll get some of the spare ones. So basically, we call it like the demilitarized zone, or it's called the depletion zone. There's really no net charge in the middle. So nothing is going on right now. Alright. Now we'll supply a DC voltage battery, whatever, and we'll put the positive to the P material, and we'll put the negative to the N material. Well, this is a condition we're going to call forward biased, because now we're in a condition where the spare electrons will come through, be drawn through our material, onto the positive side of the battery. So we'll actually have a current flow through it. Likewise, in this case, we connect our power supply in the opposite direction. It's reverse bias because now we have the negative going to the P material and the positive going to the N material. So our spare electrons are being kind of drawn away, and here we are. Our depletion zone is back again. So other than maybe possibly a little bit of leakage current going through it, essentially there's no current going through it and it's shut off. And here's our diode. Here's our schematic symbol. You always have the, whatever reason, basically an arrow pointing to the cathode. So the anode is always the arrow, cathode is always the line. If I actually handed you a diode, typically there'll be a white band or a band on the one end that's always on the cathode end. Sometimes you'll actually see they may actually be tapered or chamfered on the end. Again, that's indicating the cathode end. And then you see the innocent conductor. Electrons flow from cathode to the anode. In order to conduct, it must be forward biased. And we'll talk about this in a couple of minutes. We'll see we actually have a use for these diodes. These actually work as like a gate. And like I said, here's just a few pictures of typical diodes. Like I said, typically you see the band on the end being the cathode. Those are some of the shapes and sizes. Obviously, the higher current ones are bigger. Like actually, I was going to bring one in tonight. I had a 300 amp one home somewhere. It's got threads on it about that big. We'll look at that later. That's just showing a power supply circuit with some diodes in it. That slide pop. That's a pop. That's a power supply from a Commodore computer, for those of you who remember that far back. And now we talk about a special kind of diode. Well, first of all, let me backtrack a little bit. Normally, when we forward bias a diode, it's not perfect. So you're always going to have a little bit of internal resistance. So you will have a bit of voltage drop, a forward voltage drop, because there's always a little bit of resistance in it. So typically, there's two types of diodes mainly out there. You have a germanium, which is the material it's made of. It has a forward drop of about 0.2 volts. And silicon has a drop of about 0.7 volts. And that's typical for most. What they also have is diodes have a rating. You'll also see that they can only withstand so much reverse voltage. It's actually the specification you'll see is called peak inverse voltage, or sometimes PIV value. That's the amount of voltage it can withstand in reverse without actually being destroyed. Because if you exceed it to a point, it'll just break down and short. Talk about that some more then. With the one exception being, they call it Zener diode. It's actually designed to, well, they say in brackets, break down. Well, it doesn't destroy it. It actually will conduct in reverse at a certain voltage. So Zener diode has a rating which is called a Zener voltage. Well, it will actually conduct in reverse at that voltage. We can use that to our advantage. As you're showing here, here's a typical circuit. We can actually use it as a very simple regulator. You know, as you can see, actually the positive is actually connected in reverse there. And one other thing I'll just mention, it's in the book, they call a varactor diode. It's actually, characteristics of it is that the internal capacitance of it changes value with the voltage. You'll get into that later in other circuits. They can actually use it for tuning circuits because the fact that the capacitance will change with the voltage. We'll just mention it because I just mentioned it there in the book. Another type. And again, another use for diode you'll get into later when we talk about receivers is demodulating or detecting the audio signal out of a radio wave. You've all probably heard of the old days of a crystal radio where basically they all have very simple circuit with a coil, a diode, a little capacitor, a resistor, some earphones. You tell how old that ad is. $1.79 or something. I actually had one of those as a kid myself. It's kind of neat sitting there with nothing more than a couple of little components tuning it, and all of a sudden hearing an AM radio station. And the latest diode we're all familiar with now, LEDs or light emitting diodes. So whenever they're forward biased, they conduct and they give off light. And there you have all shapes, sizes, colors. Really neat now. I've got several of them now, and I like them way better than the compact fluorescent curly bulbs. Anyway, so how are we doing so far? Any questions or lost anybody? So we have P material, N material. Basic diode is a P-N junction. Forward bias and it conducts. Reverse bias it shuts off. Just like a gate. Alright, next along, we'll just take this a little step further, talk about a transistor. So, actually I thought I had this beat, I thought I had the presentation all ready to go and I couldn't find it so I didn't do it last week. So we'll start off just like, we'll just carry it one step further. So, just like we talked about a minute ago, there's some N material, there's some P material. A little different, there's our P-N junction, there's just like a diode. But now we'll take it one step further and we'll add a third layer. We'll add another piece of N material. In this particular case, we'll talk about this is what they call an NPN transistor. And here's basically a equivalent circuit to it. Here's a schematic for it. So likewise, just like we had with our, is this good enough or am I going to draw it a little bit bigger? Good. Okay. So again, with no voltage is applied, take and we for our diode, good thing that's so far. Here's no different we talked about before. There's our diode junction. We put our we forward bias it. Now we'll be depletion zones here. And we'll have our current flowing. So if we take so we got conduction here. So now if we put increased a bigger amount of forward bias across the transistor, we've already got current flowing here. These electrons are already moving, so they'll just keep coming through and be attracted to that higher positive voltage. So now we have conduction through the transistor. So the big So we have our three components: base, emitter, collector. So in other words, the emitter emits the electrodes, the collector collects them, and the base controls the flow. We'll talk about that a little bit in a minute. So what we have here is we have a fairly small voltage here, enables us to control this big current through here. So this is acting as a control point, basically turning it on and off, allowing the main current to flow through the transistor. Likewise, if we were to use the other variation called the PNP transistor, it works the same way except your voltages would be reversed, because we would have to put our negative voltage on the N material. And all we have is basically three level, like a diode stacked with an extra level on it. And we can talk about what we can do with that down the road a little bit. So what we can do by basically a very small change here, a small voltage will turn this on or control it. So it will actually, the little bit of control will cause a big change in the output. So just to show you, we can take that to our advantage. Here's a simple amplifier. So what we can do is take a small input voltage here, in this case there's 0.25 volts peak to peak, and the amplified comes out as 2.5 volts peak to peak. So by making a small change on the base emitter junction, we affect a very big change effect of the emitter. So we can use that to our advantage to amplify signal. In this case here, we've got a gain of 100. So in other words, the output signal is going to be 100 times the input. This effect is known as amplification, to increase the amplitude. Put that on the memory because I'm sure that comes up a few times in the question day.
Why does that occur?
What's that?
I don't understand why that amplification occurs.
Okay.
Like in terms of the PN.
Okay. So far, this is just a diode junction. Okay. So as soon as we have a positive voltage on here, but and like you say, there's our diode junction with it's always the arrow with the VD in it. So by putting here, in this case we have a 2.6 volt bias on here. So that that's forward bias, so that's conducting. But the nature of transistors, so now, over here on the collector, we have twice the amount of voltage. So now, once we have the electrons flowing through it, some of them are attracted here, but now you got a whole lot more positive here. So once those electrons are moving, most of them get attracted right through to the higher positive voltage.
So do you get a combination of the 5 volt and the 9 volt going through, or just the 5 volts?
Actually, well no, what you're showing here is the fact that you've got a resistor in series with the emitter. So that the fact that the emitter is going to be sitting at 1.9 volts above ground right here. I follow this. There's no real absolutes. There's no such. Generally, it's not so much as an absolute positive or absolute negative. It's always talked about with respect to. In other words, this point is 1.9 volts with respect to here. So in other words, this point is more positive than that point. And likewise, this point, this isn't pure negative. It's a positive voltage with respect to ground, but this is higher, so it's positive with respect to this point, right? It's more positive. And again, this will probably be a pretty good question like the end of the test. Those are your schematic symbols. And the arrow is always in the emitter lead, with the arrow always pointing from P to N. P to N, so therefore we have N, P, N. And likewise, we have P, N, P transistor.
So the arrow points from P to N, you said always?
The arrow always points from P to N. Just like in our diode example. That's always, always, always. That's how you can always tell the emitter lead, because that's the one with the arrow in it, and the direction the arrow tells you the polarity. It's always the base, the guy in the middle is always the oddball. Both outside ones are always going to be the same. If you have N and N, P in the middle, or you have P and P with an N in the middle. And there's typical example of just some little small signal transistors, pictures. And there's up in power, we'll have some bigger ones. Any more questions? Kind of move along a little bit. Move along kind of quick. Just make sure that covered everything. Maybe just backtrack a little bit here. Just a few points that weren't in the book that I just thought we'd make kind of information. When we talk about our sine wave, so typically you plug something in our receptacle. Normally we say that it's 120 volts AC. That's a comment. But what that actually is what is, to clarify it more, it's usually, correct, is that it's 120 volts AC RMS. You want to know if that's a mathematical term, stands for root mean square. Don't need to worry about that. What it is, that is basically the equivalent voltage, because it kind of averages out the cycle, because this is basically 1/60th of a second. That's kind of the average. So that's the equivalent to DC. So they had to come up with a value. For example, if say we had just a piece of resistive electric heater. So that value would give you the exact same amount of heat, the same amount of current, as if it was 120 volts DC. But, so that's the value. But actually, in fact, we looked, this value here is called the peak value. So, in this case, for a 60 cycle sine wave, the RMS value works out to be, you don't need to know this, but 70.7% or 0.0707 of the value of this peak. So, well, actually, this peak value here is actually, if we measure that within the scale in time, would actually be 169 volts. The reason I'm saying it, remember we were talking a few minutes ago, I said one of the specifications of a diode was peak inverse or peak reverse voltage. So now if you're using that in a circuit, 120 volt circuit, we're going to rectify. You have to remember now, that diode doesn't only see the 100 volt, it actually sees the peak value. It actually sees 169 volt peak value. So you have to take that into consideration when you're actually, if you're actually making a circuit or something. That make sense?
Mm-hmm.
So there's basically two specifications. If you were to go and buy a diode, you want to know how much current it can handle when it's conducting, and how much reverse voltage it can stand, or the peak inverse voltage it can stand when it's shut off. So those are the two values you need to know when you go out and buy a diode. I know some of this stuff may be on the test, but I'm just throwing in as kind of a little bit of interest and maybe a little bit of background.
200 volts?
Yeah.
Yeah.
It's just something you have to think of. Like if you were putting on a circuit, you say, well, no, that diode isn't going to see 120 volts. It's actually going to see 169 volts
But
at a peak when it's...
that would be a fair enough distance, so 200 volt would
Yeah.
be sufficient.
So you got to make sure you're bigger than that. So in other words, you'd have to be bigger than 169, not just bigger than 120 to be safe. Alright, next we're going to talk about a different type of transistor called the field effect transistor, or an FET. They're a little bit newer, they have advantages, and different information. There's two major types of field effect transistor. We have the junction field effect transistor, and this is only for the metal oxide semiconductor, which is called MOSFET in short. And they are built a little differently, and they work a little differently. In this example, like we're showing on the board, we have on the base, we just have one big piece of thin material, and on it, and also we also have so remember in our bipolar transistor, we had to apply a bias to the voltage to the base to make it conduct. In our field effect transistor, since we don't have a PN junction here, there's nothing. we actually conduct current. If we put, in this case, so actually apply a bias. So in other words, without any help, this guy will conduct. And again, we call our connections a little bit different on it. We call it the source, which is kind of equivalent of the emitter of the other transistor. So that's where we source our electrons, and we drain off or we collect them on the drain. So if I was to do nothing right now, this thing would be conducting. So what happens, why they call it a field effect transistor. So now when we start putting a bias voltage on here,
We're leaving, but I feel the coffee downstairs, the black one, the coffee pops off.
we actually start creating a field, a force field in your Star Trek movies, whatever. The more bias we put, we make that a little bit bigger. As we increase the voltage, that field keeps getting bigger. Keeps increasing the bias to the point where the field completely stops the current flow or pinches it off. Just as if you took a hose and pinched it, no water gets through. So actually, that's what they call is the pinch off voltage. When you reach that voltage where you've actually cut off the current flow, you reach the pinch off voltage. So that's what they call a field effect transistor, because we're actually creating a field in here which prevents the flow.
And the current slowly reduces, or is it
Well, it's whatever you do. It's however you want to change this voltage. At this very voltage. As you increase that voltage, that field just keeps getting bigger and bigger and bigger, so it gets to the point where it just pinches off the flow. So that's why we call it a field effect transistor, because of that little field it creates. And a third on, I didn't mention, but it's called the gate connection. The connection is made on both sides. So showing actually the gate makes a connection to the material on both sides. In other words, here's your schematic symbol for it. The source, gate, and the drain. And again, same rule applies. The arrow points from the positive to the negative. So by looking at that, obviously, so we're going to say, okay, the gate is P, so therefore the other has to be N. So then we're going to call it, it's called an N-channel FET, because the channel is all made of N material. Likewise, the opposite would be called a P-channel FET, where the main channel would be all P material, and the gate would be N material. Okay. Oh, that's what it is. There's some pictures of some typical power transistors. Slide over. Okay, junction field effect transistor. There's the symbols for them. Again, as I was saying, P channel, where positive is, I was saying the positive is the channel, P is negative, so that's a P channel FET, and likewise P pointing to the N, so the N being the channel, N channel FET. And again, our three terminals, gate, the drain, and the source. That you will have to know. again, I'm section 9.5, they talk about gain, I mentioned that before. Any amplification or amplifier circuit is gonna have gain, which is basically the difference of the output over the input. In this case, we had, 2.5. Gain of 100. And that's a word they'll, I've seen in some of the exam questions, they play on words is the process known as amplification. They give you a choice of words. And well, that usually shows up in the question. Alright, and again, as we were talking about before with diodes, just carry a little bit further, some of the characteristics or specifications for a transistor. Talk about a breakdown voltage, which is basically the maximum voltage you can apply between the collector and emitter or any of the terminals without doing damage, to the point where it does damage. And maximum, and also they talk about maximum current, the actual maximum current that you can pass through from the collector to emitter without damaging it. And the maximum, when they talk about the maximum power, it's how much it can handle. Otherwise, it can get, if you exceed the rating and you try to push too much current through it, it gets hot, and they get into a condition where, you mentioned it's called thermal runaway, where it just, you lose control and you can't shut it off. It just goes until it burns up. And I see in your book, there's quite often you'll see a transistor, a power transistor, in order to help it cool off. They have they'll mount it on which is a piece of metal with fins. It's designed to take the heat away and put it out into the air. And I'll just talk about it briefly. Integrated circuits, really all it is in most cases. It's a block. They've perfected it more and more, where they take a block of silicone and they laser etch it or whatever they do it, and they actually create little transistors and stuff all in one block, and then inside of one chip you can have multiple transistors and that.
Is that all the ICs are, is just transistors? Or
No, they actually can. They can make. They can actually make resistors. I guess they can just about do everything inside them by wherever they manipulate the silicone base or whatever.
So could they like install diodes in there as well?
Yeah, they can create whatever they need to. Whether they do it's a doping, I don't know how they do it. It's so miniature that I have no clue how they would even do it, but they do it.
I thought it was just transistor based.
No, it can't be more. They take that base and they do all kinds of wonderful things to it. You have pretty amazing circuits inside the integrated circuit. Well, typical microprocessor now, no, it's all in one big integrated circuit. More questions? Or go on. All right. I guess next we're gonna actually almost, in a way, kind of take a jump back in time. Vacuum tubes. Those were our very first active devices, kind of predating our transistors and semiconductor diodes as we know them. Probably, some of you probably seen some of them back in the old days where your television and stuff was just full of them. And
Now with guitar amps.
Yeah, they still use them. There are actually some.
There's the biggest push for them. That's how.
There is some audio purists that say that the tube amplifiers have a different quality or different sound, and
And all the hipster kids are using the oranges. And all
yeah,
the film too. So it's actually it's a lot more popular than the solid state.
yeah. I guess they have their characteristics, or and up until more recent times, tubes were still very prevalent in big transmitters and stuff because they hadn't got semiconductors or transistors to the point where they could handle the power. For a lot of times, even up to most recent, it was they'd have a transmitter or transceiver, we'll call it, which is a combination of transmitter and receiver. It would be all solid state up until the final amplifier, and then it'd be tubes because the transistors at the time just couldn't handle the power. Now they've kind of gotten over that, but
I even use a tube preamp before I go with my video.
yeah.
So I use a 12 ATX 7.
Okay. Well, actually, it's up.
It's close enough.
Yeah, very close. So let's take a quick run through. By the way, for whatever reason, our friends in Britain call them bells because the very first electron tube was simply a diode. So it actually, in a sense, a diode acts as a valve. It lets things go one way, not that. So anyway, it's stuck, and even to this day, they still refer to them as valves. If you find any kind of English technical literature and they're talking about valves, well, just think in our mind, well, we call them vacuum. And really, why we call them vacuum tubes is they're a tube of glass. Inside it, we have a little heating element called filament, and surrounding that, very typically, it's like usually it's a little tube or whatever called the cathode. And so what we do, filament. So we put power to our filament, to low voltage, and it's just a heater. One of the conditions, when you heat this element, especially when this is all in a vacuum, when we heat this cathode, this little metal tube, it tends to start having loose electrons. So, in other words, the term they call is thermionic emission. When you heat it up, it starts giving off loose electrons. So, once we get this heated up, so we have this container full of loose electrons looking for somewhere to go. Alright, so this is schematic symbol for a vacuum tube diode. So again, just like our semiconductor we talked about, same two elements, we have an anode and we have a cathode. The only difference is now we have this filament, so we're applying heat to it. So now we have our little heater going, we're heating up the cathode, we have loose electrons available. So now we have our anode, or actually it's a plate, and that's why they kind of call it a plate. So our plate. So now, as soon as we forward bias it and put positive voltage on the plate with respect to the cathode, it's going to conduct, just like our PN junction did. So when it's forward biased, it conducts. And likewise, if we were to reverse our voltage and put a negative on the anode, and put positive voltage on the cathode, then all those loose electrons are going to be kind of pulled back to the positive. So then you're not going to have any current flow or any electron flow between the two elements. Oh, it even mentions in the book, some parts of the world tubes are called valves. This is really, I guess if you want to take it that far, they can say it's acting as a valve, it's controlling the flow. So we'll take this one step further now. And we'll introduce another element. And by the prefix, we can tell them apart. So die always, the prefix of die means, it always refers to two. So now we're going to talk about the next thing, when a triode. So triode being three, we're going to have three elements now. Okay, so now we've gone one step further. Here's our diode, but now we can create a mesh grid in it. Just to refresh, you should probably know it, but just to refresh, battery is always shown, the convention is the long stroke or long bar is always the positive, the shorter one's always the negative. So here we take, there's our old semiconductor, our vacuum tube diode, no different so far. Before we bias it, we've got it heated, so now we have our electron, we have current. So if we were to come by now, and we'll put a bias voltage on our grid, control grid it's called. So you notice it's reverse. So we put a little bit of negative voltage on the control grid compared to the cathode. So now we're starting to almost act like our old field effect transistor. Because what's happening now, this now is sitting at a negative potential. So now all of a sudden some of the electrons that are coming here are going to see the spot, the negative, and they're going to get reflected backward, and they're not going to get through. So all of a sudden our current flow is going to be reduced from the cathode to the anode, right? And if we bring this voltage, make it negative enough, or in other words, bias it off enough, it's just going to be just like in our field effect transistor. We're going to essentially pinch off or cut off the flow. In this term, it's called the cutoff voltage, where we actually put enough negative voltage here where all the electrons are going to get repelled back and we're not going to get through. So that's how we can control it. And we can use this again, just like our others. If we were to work through a circuit, if we actually applied a changing DC voltage on the control grid, a small change on the control grid would make a big change on the anode. So again, that's how we can use it for an amplifier. But just making a small change on control affects a big change on the increment.
Wouldn't you have to reverse that small voltage on the grid? Wouldn't that have to be reversed to make it amplify?
No, because you vary the point where you have it conducting to a certain point, but you actually have the signal varying it up and down. So in other words, as your voltage goes on more, as it goes one way, you'll actually let your conduction increase, and as it goes the other way, it'll increase and decrease the current. No, so you'll actually have it sitting at some point, and then you apply the AC on it, and it will just vary. You don't have it turned all the way on or turned all the way off. You just have a point.
say you had the outside voltage, there was, say call it 4.5 volts there.
Okay.
Right? It's a volt and a half each.
Okay.
And you had two cells equivalent to 3 volts on the inside. Is there a way of saying roughly what the, or I don't even know if we need to know.
Okay, so let's just say, vacuum tubes, one of the maybe this then is the fact that you talked about you need a lot more voltage, you're running higher voltages. So typically on this circuit, you would have something like perhaps 200 volts on the anode plate. And here on the control grid, you might have something let's see. So maybe I'll say 10 volts or something minus 10 volts. So that would be saying at a point where it's conducting, but it's not conducting fully. We're choking the flow off a little bit, but now we apply our little signal here, little AC signal. So now,
What voltage is that at, say, that signal?
it would be maybe part of a volt, or whatever. It would be small with reflect to the bias value. And so at this point in time, so when it goes negative, we'd actually say at that point in time that voltage goes to just at this instant in time. Well, this is +1, -1. So this instant in time, +1 would add that to your -10. That would actually make it -9, right? So now, by doing that, we're actually going to let more electrons through. So our current through is going to increase, right? Because we've reduced that control voltage, now we're not blocking the flow as much. So in other words, so now the net current going through it is going to be bigger, right? Because we dropped that bias, dropped it from -10 to -9, which is a smaller voltage, putting less control on it. So now we'll see the output going to have more current through it, so we'll actually have an increase in the current flow through it, right? So likewise, this point in time right here, they only have -1 volt. We're going to increase that reverse bias to -11 volts. So therefore, we're putting more control, more negative voltage. We're reducing the current flow. So likewise, the current through it gets less, it's reduced. I'm just kind of picking numbers, but that's just reflective. Does that answer your question? And there's two other tubes I'll just mention, just for the anyway. They call them multi-electrode tubes. If we add one more element with another tube called the screen grid, I think it is. It's called a tetrode. And I'm looking at the section 9, somewhere. And the other variants would be, add one more, it's called a pentode. We've noted that a suppressor. I don't think they ask much about those questions, but anyway, that's the thing. 2 elements is diode, 3 elements triode, 4 elements is a tetrode, which is kind of rare, and more common, the 5 element will be a pentode. And just saying about some thoughts about tubes. One thing about them is the fact that tubes are fragile, they break easier. You need a lot more voltage. You need a way bigger power supply to deal with them. In some cases, 200, even in some cases up to like 400, 500 volts. You need to run a power amplifier. And the big thing about it is heat. They can generate lots of heat. And that was one of the biggest problem with that, with tube devices, all the heat in the chassis would cook things. Like the capacitors would dry out and things would happen over time, mainly due to the heat factor. As an example, just how it worked back in my early days, I worked on the broadcast transmitter at 1050 in the AM, and it was a 10,000 watt tube transmitter. The building had no heat in it. As long as the transmitter was on, it was comfortable as anything in the middle of January. Turn it off for any length of time, because typically we do maintenance like after midnight. Shut it down, and within a very short time, it started getting awfully cold in the building. But typically, that was the big thing about tubes, was the heat. And just to put it all in perspective, okay? Here is the comparison I think you missed can pick up here. Basically, the schematic equivalents of the three devices we've talked to so far. The tube, bipolar transistor, the field effect transistor. And the element, typically, that's questions. I was going to, when we do for the review, I'll get some typical questions out of the book. Basically, it's going to ask you what's the three elements or the three terminals of a tube. You know, in this case, it's a child. You have the cathode, you have the control grid, you have the anode or plate, and that's the three main elements. You may ask about development. Likewise, on a bipolar transistor, you start with the emitter, base, the collector. The field effect transistor, you have the source, the drain, and the gate. So in other words, this is showing the equivalent. So in a tube, the grid is effectively the same as the base on a transistor or the gate on the field effect transistor. And the drain is basically equivalent to the collector or the anode or plate on our vacuum tube. Just put it in perspective, compare the two devices effectively. And that is our Reader's Digest version of active components. Questions? Comments? Ready for coffee? Do we actually have coffee here?
Yep.
8 o'clock, so it wasn't bad time.
Perfect time.
I hope that is clear. Get questions, we'll deal with them, but that's the highlights of
Coffee's made and it's ready downstairs.